Hello and welcome. In this video, we are going to talk about transformations and how they impact quadratic functions. Chapter 2 is all about quadratic functions. And in this section, we're going to take what we learned in Chapter 1 and focus on how do those different transformations, whether it's a translation, a reflection, a stretch or a shrink, or a combination, how do those affect the graph of a quadratic function? So let's go ahead and jump right in. All right, so a quadratic function is a function that can be written in this form, and this is called vertex form, and we will be specifically going into the details of vertex form in 2.2. But a quadratic function is basically a function that the degree is 2. Quadratic function. When we graph a quadratic function, the U-shaped or upside down U-shaped of the graph is called a parabola. So in previous classes, you've also talked about this notation, which is called standard form, which we'll talk about as well in this chapter. But we're going to focus today on identifying transformations, and we're going to be using this form, which is called vertex form, which again we'll formalize a little bit more in the next section. So how do H and K, how do changing these two components impact the graph? Well, that's where our translations come in, right? X minus H, or having a number inside here, we talked about in Chapter 1, how that could shift the graph left or shift the graph right. This is horizontal, and it's happening inside the function, high vo. So if that number, as we talked about in Chapter 1, and remember that what we see on the inside of that function is it's the opposite of what we think. So if we saw x minus 2 squared, minus 2 actually means that we would be moving 2, translating 2 to the right, versus if it said x plus 2 quantity squared, we would be translating 2 to the left. So horizontal happening inside. Vertical things are going to happen on the outside. So notice there's no parentheses. There's nothing inside with x here. It's this plus k, and vertical things happen outside, and they are what we think they should be. The vertical is the original. So plus k means up, minus k means down. And what happens when we shift our graph up and down is that we're moving the vertex, all of the other points as well, but in terms of if we're going to be graphing, the first thing that we want to graph is where is our new vertex based on this transformation. So a translation impacts the vertex, and I will say it impacts all of the points as well, but if we are graphing, we want to shift that vertex and then use what we know about the parent function to graph the new transformed quadratic function. And the vertex is just that highest or the lowest point. So if it's opening downward, this would be the maximum or the highest point, versus if it's opening up and down, this would be the minimum or the lowest point. So let's go ahead and look at a couple of graphing problems and see how we can use what we know about transformations to graph a quadratic. Okay, so let's first identify the transformations that are happening here, and then we can use that to graph our transformed function. So this plus 4 on the inside means that we are translating 4 to the left, and this minus 1 on the outside means that we're translating 1 down. So sometimes it's helpful to graph the parent function. So I'm going to just quickly in red graph the parent function here so that you can see. Ooh, I graphed that last point wrong. There we go. So that you can see how to move each of these points. So every single point I'm going to move it 4 to the left, and then I'm going to move it down 2. So I just want you to think about it. I'm moving 1, 2, 3, 4 to the left and down 2, and that's where my new point is going to be. I'm going to erase that so we can see it a little easier. Then I'm going to go to the next point. I'm going to go 4 to the left, 1, 2, 3, 4, down 2, and make a point. I'm going to take the vertex. I'm going to go 4 to the left, 1, 2, 3, 4, and I'm going to go down 2. And I'm going to do that with all 4 of the points, all 5 of the points. You don't have to graph the parent function. If you're comfortable enough and you know the shape, it's okay. If the directions don't specifically say to graph the parent function, it's okay for you to just graph the transformed function. So let's see what that would look like here on number 2. This -1 means that we're going to translate 1 to the right. And this +2 means that we're going to translate up 2. So where is my new vertex going to be? If I'm not going to graph the parent function as well, then I'm going to graph the vertex first. So the vertex is normally in the parent function 0, 0. But now we're moving it 1 right and up 2. So my new vertex is going to be here. There are no other transformations happening, so there's no stretches and shrinks, there's no reflections. So this is going to hold the same shape that it would normally hold if I graph it at 0, 0. So I can just plot where those next 2 points would be, and I can connect to make my curve. Make sure you read the directions sometimes, and some teachers are going to ask you to label specific things on the graph. These directions are just asking us to graph the transformed function. So let's talk a little bit about stretches and shrinks now that we have talked about translations. So reflections and stretches and shrinks. This is exactly the same kind of thing that we talked about in chapter 1. So reflecting across the x-axis is going to be this red graph, so it's opening downward instead of opening upward. You see that happen on the outside of the function, as opposed to on the inside of the function, you're going to see the reflection in the y-axis. And you'll notice that the parent function, if we reflected across the y-axis, is actually exactly the same. That's not true for every function, but it's true for the parent function of the quadratic. Now, horizontal stretches and shrinks. What I want you to think about is how you're doing things in relation to the x-axis. So a horizontal stretch is like you're pulling the quadratic, you're pulling it away from the y-axis, you're stretching it out. That would be a horizontal stretch. A horizontal shrink is like you're pushing it, you're trying to make it smaller and smaller and smaller, you're pushing it towards the y-axis. So a stretch is going to happen when a is between 0 and 1, and a shrink is going to happen when a is greater than 1, or I should say when the absolute value of a, because we're not talking about positive versus negative, that's reflection. A vertical stretch, same concept, except now we're thinking about how we're doing things along the y-axis. So if I'm stretching something vertically, it's like I'm pulling it up and down, pull, 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 versus shrinking, I'm pushing it together. And this is a little counterintuitive because a lot of times the word shrink makes me think something's getting smaller, and in our images, it's actually getting fatter, but smaller in the way of how it's approaching the axes. So a vertical stretch happens when a is greater than 1, and a shrink happens when the absolute value of a is between 0 and 1. So let's talk about how to use these stretches and shrinks and reflections to graph our quadratic functions. So one thing that I'm going to say is that if you are just translating or just reflecting your graph, then I don't necessarily think that you need to make a table. But if you have a stretch or a shrink, you should probably make a table. It's going to help you find your new points. So if I look at number 3 here, and I am going to go ahead and make a table after I identify my transformations, that negative in front is telling me that I'm going to reflect across the x-axis, which I'm also going to make a note to myself means that this quadratic is going to open upside down. The 1/2 is a vertical shrink by a scale factor of 1/2. So notice we're not translating, and what that means for our graph is that the vertex is still at 0, 0. So if I'm going to use that information to graph, I'm still going to use... Actually, I'm not going to use -2. I want to use some even numbers so that it's going to be easier to graph. So I'm going to use -4, -2, 0, 2, 4. And we already know that 0 is 0 because that's the vertex. So I like to have my vertex right here in the middle of the table. If I plug in 2 or -2, I'm going to square that to get 4 and multiply that by -1/2 to get -2. So I can go ahead and plot those 2 points. And I'm going to do the same thing with 4. If I plug in 4 or -4, I'm going to square it. That's going to give me 16. -1/2 times 16 is going to give me -8. And I actually think this is going to be just off of the graph, which is okay. It'll give me enough to give me the shape. So then I can connect my quadratic. Okay, for number 4, we have something happening inside, so there's a horizontal shrink by a scale factor of 1/2, and there's a translation up 1. So my vertex is just moving up 1. So my vertex is 0, 1. So I'm going to put that in the middle of my table. And I'm going to just put numbers around. So if I plug in 1 or -1 and square that, I'm going to get 4. 2 times 1 squared is 4, plus 1 is 5. So for both 1 and -1, I'm going to get 5. If I plug in 2 or -2, I'm going to get 4 squared is 16, plus 1 is 17. That point is definitely not going to fit on the graph. So I'm going to just go ahead and make sure I graph the 3 points that will fit here. And then I'm going to connect and make my thinner U-shaped, right? That makes sense based on the fact that we have a horizontal shrink. Let's look at 2 more graphs. So I'm going to encourage you to pause the video, identify the transformations on your own, and then make a table after you graph that vertex. Then unpause the video and see how you did. So here's my first step. Hopefully you had enough time to try this. I identified the transformations and I plotted the vertex. Now I'm going to make tables for each of these values, and I'm going to choose values on number 6 here that are going to give me not fractions as my answers. But go ahead and work through the rest of this on your own if you haven't already. And there we go. After I completed my tables, I sketched my graphs, and there we have it. So with stretches and shrinks, it's not so easy to see what that transformation is going to be, but we can still use what we already know about quadratics to graph them. All right, the very last thing we're going to do in this video is talk about how to write transformations of quadratic functions, and we're going to focus specifically on vertex form. So we're going to define it, and then we're going to apply transformations. The lowest point on a parabola that opens upward, lowest point, or the highest point on a parabola that opens downward is called the vertex. Now this is a term that we have already been using, but we're just formalizing it here, and we're going to formalize vertex form, which is what we see right here. So when we have a quadratic written in vertex form, it's really helpful because we can right away identify the vertex. So for example, if we had f of x equals 6 times x minus 1 squared plus 7, we could immediately identify that the vertex is the vertical translation and the horizontal translation. So horizontal first, the horizontal translation is 1, the vertical translation is 7. So right away we can immediately pull out what that vertex is, which is super helpful whether we're graphing or using it to solve a word problem. We can also identify, I'm going to change this to be a -6. We can also identify whether the quadratic opens up or down. So that negative would mean that there's a reflection in the x-axis, so it would open downward. And this 6 would tell us about our vertical stretch by a scale factor of 6. We're going to really heavily focus on identifying all of these different transformations from vertex form in the next video, and how to use that to graph and how to use that to write a function. What we're going to do in this video is we're going to talk about identifying the vertex after we apply a transformation. So let's go ahead and focus on the transformation aspects and use it in vertex form when we have it. All right, so here we go. The graph of a function g is a vertical stretch by a scale factor of 2 and a reflection in the x-axis. So let's apply those first. G of x is vertical stretch by a scale factor of 2 is 2 outside, reflection in the x-axis is outside. So that's what's happening first, followed by a translation to 3 units down. So the first question I'm asking myself is, do I have an issue with order? Am I supposed to stretch and reflect and then translate? Yes, I am. So a little happy face here, we're all right. So now I can just apply my transformation down 3. So I'm going to go ahead and write this in terms of this function. So where there is an f of x, I'm going to put parentheses squared. I'm going to bring my stretch and reflection down. Apparently for this function, x is still just x, and I have minus 3. So here is my transformed function. Now I'm going to rewrite this just slightly so you can see how we could have this in vertex form. And now we can identify our vertex. Here's my h value. So the vertex is going to be 0, -3. I encourage you to pause the video and write both the function notation, the actual function, and then see if you can identify the vertex on number 8. Then unpause the video and see how you did. All right, hopefully you had time to work through number 8. The graph of G is a horizontal shrink of 1/3, so that means 3x on the inside, and a reflection in the y-axis, which is also on the inside, followed by a translation 2 units up. We don't have any order issues here because going up is the only thing that's happening vertically, so it's not happening out of order. So our order is okay, smiley face. Now I can apply that to my function. G of x is, my function is x squared. Everywhere that there is an x, I'm plugging in -3x and I'm moving up 2. Now I want to identify that vertex. Well, there is no horizontal translation happening inside, so the x value of my vertex is still 0. The translation that's happening vertically is 2, so the y value of my vertex is 2. There's one last thing that neither of these examples did that I just want to show you, and that would be, what if we had a transformed function that maybe looked more like this? And I asked you to find the vertex. I know you could list the transformation correctly. You could list that we have a translation 5 right, a horizontal shrink of 2, and a translation up 7. But if I asked you just for the vertex, how would you do that? Well, what you would do, the vertex is going to be how this has changed from its original state of just being x. So what you can do to identify what the x value of the vertex is you could just set the inside equal to 0 and figure out what value makes that equal 0. So I'm going to add 5. I'm going to divide by 2. So the x value of the vertex is 5/2. The y value is just this 7 that's outside. So if you have to identify the vertex and there's something happening horizontally besides the translation, because if you remember, in vertex form, the only thing that's supposed to be inside happening horizontally is the translation. So if there's something else happening inside, you can still identify the x value of the vertex. Just set the inside equal to 0 and solve for x. That'll give you your x value. So I know that wasn't on here. I just added that in because I wanted you to see how that would work. We're going to look at 2 last examples that are not going to be in vertex form, and I want you to see how, if we're not transforming from the parent function, what that looks like. All right, the first thing I'm going to encourage you to do is just pause the video and write the function notation version for both of these first. Test yourself, see if you can identify if there's an order issue or not, and then unpause the video and see how you did. All right, so number 9, g of x is a translation 3 units to the right. So that's f of x minus 3, and 2 up, so plus 2, followed by a reflection in the y-axis. So I'm asking myself, do I have an issue with order? No, I don't, because I am supposed to translate and then reflect, so I can just plug a negative in here. So no issues with order. If we look at number 10, g of x is a translation 4 units to the left, so that's going to be x plus 4, and 1 unit down, followed by a reflection in the y-axis again, still not out of order, so we don't have any issues here. So now that we've written the transformation in function notation, let's go ahead and go back and actually apply this to the function. So this function on number 9 is f of x is x squared minus 5x. So remember, we're replacing the f part with that function. So I have something squared minus 5 times that something. That's the f part. Now, according to this transformation, we are supposed to plug this in everywhere that we have an x. In this particular problem, we have x in 2 places, right? We have x being squared and we have -5 times x. So inside these parentheses, I'm going to put -x minus 3. And inside these parentheses, -x minus 3. So that's coming from, this is telling us what to plug inside for our x value. It's like you're saying x is actually equal to -x minus 3. This says, first, take f, plug in -x minus 3. Now, after we've done that, we're going to add 2. So after I've done this, now over here, I'm going to add 2. For right now, I'm actually okay with you leaving your answer like this, but let's just expand it out a little bit. If I multiply this binomial out, if I multiply -x minus 3 by -x minus 3, I'm going to get x squared. Actually, I don't need parentheses here. I'm going to get x squared negative 3x, negative 3 times negative x twice. That's going to give me x squared plus 6x plus 9. If I distribute this 5 here, I'm going to get plus 5x plus 15, and this 2 is going to come down. So I can simplify this to be x squared plus 11x plus 26. Now this is in standard form, and we're going to review standard form next class. So right now I really just care, can you get that transformation? Can you plug it into multiple pieces when you need to? So go ahead and pause the video and try and apply this transformation in number 10 to our function g. All right, hopefully you had time to work through this. Our function f is 2 times something squared plus something. And that something that we're plugging into both places is this guy right here, negative x plus 4, negative x plus 4. After we do that, we're bringing this minus 1 down on the outside of parentheses there. So again, this is an acceptable final answer. I'm going to go ahead and expand. So this is going to be 2 times x squared minus 8x plus 16 minus x plus 4 minus 1. I'm going to distribute my 2 to x squared minus 16x plus 32 minus x plus 3 if I combine 4 and negative 1. And then I'm going to combine like terms. 2x squared minus 17x plus 35 is going to be our simplified function in standard form. So we covered a lot in this video, but also a lot of what we covered was a review from chapter 1. So let's hit the key things and then we can go ahead and wrap up. So a quadratic function is a function that has a degree 2 function. The graph of that function is called a parabola, the U-shaped or upside down U-shaped graph. We talked about how horizontal and vertical translations affect the vertex and all of the points, really, and how we can use that to graph. Then we talked about how reflections in both axes and stretches and shrinks, whether they're horizontal or vertical, how those affect our graph. And we talked about how it's really important to first graph the vertex after you identify those transformations, and then just create a quick table to get the basic shape, which we know is going to be a U-shape, but what that's going to look like with respect to our particular problem. And then lastly, we talked about how to transform quadratic functions, which again was review from last class, but we focused on the vertex and applying those transformations in a function that is not necessarily in vertex form. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.